Yeah, so it's a pleasure to be here today. My name is Adam, and I'm an engineer. I'm a glorified mathematician, if you wish, and I work predominantly with machine learning. For the last 15 years, I've been working with different parts of machine learning, and very recently, so only for the last 5-6 years, predominantly working with neural networks. And I'll be talking today about neural networks. So the subject that you might have heard referred to as deep learning. And in principle, since we're talking today about synthetic generation, I'll be talking about models that can generate data and why they are important, why they are the future of artificial intelligence. But I didn't want to make this talk too futuristic. So after a bit of a theoretical introduction, I'll show you some real examples of things that are possible today, hopefully to inspire you and to spark further conversations. So without further ado, let's try to establish some common knowledge, some common vocabulary. And it's important to do that, because if you understand, especially the answer to this question, so why do neural networks work at all, it will be much easier for you to assess what is possible, what is not possible, and what do you need to put in place in order to build solutions like the ones that we saw earlier today. So solutions like Google system that recognizes the context of speech and adds music effects. Solution like you saw earlier, delivering parcels. Those are all systems that are taking advantage of neural networks. So why do neural networks work? And it's a very important question to ask, because neural networks are not new. We know about the concept of neural networks for at least 50 years, if not more. More importantly, the neural network that is so successful today didn't work in the 80s, even though it's exactly the same algorithm. So the tools that we use today are identical to the tools that we used in the 1980s. The backpropagation algorithm that is used today was known then, and neural networks were referred to as a failed machine learning experiment. They physically didn't work. And they are a very simple algorithm. They effectively just take the data, and that's our X. They take some labels, and that's our Y. And the only thing that they are trying to do is to find a function that maps the data to the labels. So they will take a set of images, say pedestrians and cars. They will take a set of labels, saying this is a pedestrian, this is a car, and the only thing that they are trying to do is to find that function f that maps those images to those labels. So it's a trivial algorithm, but historically, it has never worked. Yes? So in 1990s, 1980s, they were inferior to a wide range of other algorithms. And understanding why they didn't work in the 90s and why they work so well today is fundamental to being able to scope projects and think more systematically about what your organizations should and should not be doing. So let's have a look at it. So why they didn't work? Yeah. One of the main reasons why this algorithm never worked is because in the 1990s and early 2000s, the data storage was expensive. It was prohibitively expensive to store very large data sets, measured in petabytes, terabytes. Only a handful of organizations could afford a petabyte storage 20 years ago, or 30 years ago. But even if we would somehow transport a modern storage solution from today to 1990s and put it into the data center from that era, that would be fairly useless. Why? The compute to actually process such vast amounts of data didn't exist either. No, and we know all of that. We know that we have improved our capability to store the data. We know that we have been taking advantage of Moore's law, to increase the computational performance of computer systems. So in the 80s and 1990s and early 2000s, every year we would increase our compute capability by 50%. So every decade by 1,000x. And even though Moore's law has now come to an end, we are no longer capable to increase the compute by just throwing more transistors at the problem. We continue to increase our compute capability because we are smarter about the way we design hardware. And in particular, GPUs, so the hardware component that NVIDIA manufactures, allows the society to continue to grow that computational capability. We all know that we've heard about Moore's law, obviously, but we rarely appreciate just the order of magnitude of change that happened in the last couple of decades. So I would like to show you the same graph, but in a bit of a different way. So let's have a bit of a perspective look at the problem. So this building, this entire data center, in November 2009, so less than 10 years ago, constituted the world's most powerful supercomputing cluster. Yes? When this entire building was used to solve one mathematical problem, and one problem only, that entire building could deliver 1.759 petaflops, and flop is a unit of compute, floating point operation per second. So 1.759 petaflops of computational power. This entire multi-million-dollar investment could do that much math every second. Today, a single system composed of 16 GPUs, from the neural network perspective, can deliver 2 petaflops of compute. So in less than 10 years, we've managed to transform what was an entire supermarket-sized building into a single computer. And that's a massive change of a paradigm, because suddenly the computational power that was reserved maybe to 5 largest countries on the planet is available to everyone. Yes. Thanks to GPU revolution, we managed to dramatically decrease the cost of compute, and that was absolutely critical because neural networks actually use that computational resource. In fact, even with this computational power, some of the neural networks will take weeks, if not months, to train on a system like that. So this allowed people to iterate, make mistakes, and learn from those mistakes. And I really mean that they are available. You can rent half of a system like that, so 1 petaflop system from Amazon Web Services or Google Cloud or Microsoft Azure or whomever for approximately $20 per hour. So suddenly, compute that required multi-billion-dollar investment can be rented for 10, 20 pounds per hour. That's a major change in capability. And that was absolutely necessary. And the research community immediately jumped on that increased capability as it became available. So in 2015, state-of-the-art computer vision neural network, so a neural network that can recognize images, would have 60 million parameters. So if you don't know what parameters are, if you think of a linear equation, y equals a of x plus b. A and b are parameters, so you can think of this neural network as being an extremely long equation with 60 million of those parameters. And to train that neural network, we would require 7 exaflops of compute. In 2016, Baidu's deep speech, so an algorithm that, when given text, will translate that text into human spoken text into written words, will require 300 million parameters and 20 exaflops to train once. In 2017, Google Neural Machine Translation algorithm, so the algorithm that you'll use when you go to translate.google.com, is composed of 8.7 billion parameters and requires 100 exaflops to train once. And I know that those numbers are fairly meaningless, so let's look at them once again from a bit of perspective. 100 exaflops is equivalent to approximately 2 years of compute on a state-of-the-art dual CPU server. And this shows you why progress was not possible in the 90s. You cannot expect an engineering team to write a bit of code and check whether it works just to find out that it doesn't work 2 years down the line. Yeah? So those engineering iterations, they need to be dramatically shorter, and that prohibited progress. Fortunately, our capability to deliver compute increased dramatically. And now it is possible to build those larger and larger neural networks, and they simply just improve. By providing neural networks with more data and by making them bigger, we make them more performant. And that's fairly universal, irrespectively of the problem you're trying to solve. So whether you're trying to solve a translation problem, so translating, say, Dutch into German, a language modeling problem, so trying to answer questions of your customers on a chatbot, or supporting your staff in the conference center. Character language modeling, image classification, attention speech modeling, that relationship is fairly universal. The more data you provide to those models, the lower level of error they achieve, and the bigger you make those models, the better they can take advantage of the data. And we have fairly strong empirical evidence to support that. By we, I mean the academic community. So this is groundbreaking. We didn't have that 20 years ago. For the first time in human history, we seem to have a tool that can achieve almost arbitrary performance if it's given enough data. Yeah? This is not something that we had in the past, and this is what transforms extremely complex problems into easy problems. And in fact, we underappreciate how complex some of the most trivial problems that we deal with today were 20 years ago. Those filters that you saw earlier today, slimming a human face, those were prohibitively difficult to implement 15 years ago. Now they become fairly trivial, and you see them in toy applications all over the internet. But at the same time, it's transformed impossible problems, such as self-driving cars, into expensive problems. Why expensive? Because accuracy requirements mean that we need really, really, really a lot of data. So to put it in a bit of perspective, I'll show you a short video demonstrating some of the projects that my wider solution architect helped customers to develop. And I would like you to think about what do those projects, what do those algorithms have in common? One thing and one thing only.
I am a visionary, exploring a universe of data to sharpen our view of the most distant galaxies, and studying black holes to help prove Einstein's theory of gravitational waves. I am a healer, giving doctors the power to turn mountains of data into life-saving breakthroughs, identifying diseases like leukemia from a simple drop of blood, even in our own homes, and finding new ways to bring cures to market faster. I am a protector, keeping our oceans safe from invasive species, and helping our crops flourish while minimizing pesticides. I am a helper, assisting customers in stores and the disabled in their homes. I am a navigator, mapping our world 1 millimeter at a time, and making even the largest self-driving vehicles safer for the long haul. I am a creator, learning to paint from the masters and applying their styles to create original works of art. I am a teacher, analyzing 500,000 player moves every game to identify strengths and weaknesses. And a learner, discovering new strategies from complex games. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
So what do they have in common? Nothing. Nothing apart from the fact that they were all defined as supervised learning problems. So once again, y equals f of x. They required someone to collect a data set, x, set of images of plants, yes, set of images of the galaxies in the universe, And it required someone to label those data points, to physically say that this image has this plant in it. So y equals f of x. They were supervised learning problems. And it's a huge opportunity because all of the problems in the universe can be defined like that. You know, the universe is driven by math. Y equals f of x. It's a fairly fundamental formulation. So a wide range of problems can be solved with those methods. But it's also a huge challenge. Why? Because of that graph that I showed you earlier. That relationship is brutal. It follows a logarithmic scale. So it means that if you try to build an algorithm that has 80% accuracy, you need, okay, fair amount of data. But then if you want to increase it to 90%, you need to increase it, and you need to increase it exponentially. And then you want to move it from 90 to 99%. And once again, you need to increase that volume of data exponentially, and it gets prohibitive. Not necessarily the data collection part. It's really easy to collect data, but labeling, it's okay if you want to label, say, automotive information, so road sign, pavements, pedestrians, everyone can do it. But what if you want to label brain tumors? What if you want to label gravitational distortions? How many people can actually label those data sets? It is a challenge to label such vast amount of data, especially if that labeling process requires skilled labor. So is there a better way? Is there this holy grail of artificial intelligence that will allow us not to label the data? And it's difficult because that's the only thing that neural networks do. There are no miracles. They are not intelligent in any way. They literally approximate functions. But what we can do is try to reformulate the problem. So rather than making X our data set and Y our labels, how about making X just a bunch of random numbers, and Y our unlabeled examples? This transforms the problem. We are no longer training our neural network to solve a specific problem. So we are not training it to distinguish cats from dogs, but instead we are training it to learn a phenomenon. We're in more formal terms, we're training it to learn a probability distribution of a problem. And models that are defined like that are called generative models because they have the capability to generate data. Once those models are trained, you can provide a new random number, and they will imagine, they will generate new data sets, and this is what I want to show you in the last part of this talk. So a couple of examples of things that are possible today, and hopefully that will lay foundation for the future of artificial intelligence. So let's have a look at teaching machines. Teaching machines, for example, how to compose human language. So what you're seeing here is a transformer model. It's a model that is capable of generating text. And that model has 100 million parameters, and it was trained on the entirety of the Wikipedia. Minus the article about Abraham Lincoln, and then it was asked to generate an article about Abraham Lincoln. So Abraham Lincoln was an American prime minister. US doesn't have prime ministers, who was an early proponent of an anti-witchcraft situation. It doesn't read right. It's not a fluent, human-readable text, and definitely it's not historically accurate. But what would happen if we would increase the size of that model from 100 million parameters to 5 billion parameters, so making that neural network 50 times larger? Suddenly it starts to make sense. Abraham Lincoln was American lawyer, jurist, and politician. He served as the 19th president of the United States from March 1861 until his assassination in April 1865. Born in Newark, New Jersey, Lincoln attended Knox College. That's readable. It's still not historically accurate, at least not entirely, but it is dramatically better, and this is a perfect demonstration of what I was trying to show you. Just by providing those models with more data, we can make them dramatically better to the extent that we started to be really good at building language generation models. And some organizations like OpenAI decided not to release some of the details of their work in effort to protect the general public from people doing malicious things with those algorithms, such as generating huge volumes of deceptive, biased, of abusive information. But we've taught those machines how to operate human language. But there are other forms of human language. So could we potentially train those neural networks to compose music, so write notes? Of course we can, because once again, we can formulate it as y equals f of x. So that clip was generated by a machine. It was conducted by people, but the machine actually generated the notes that those people were using. Could we create other forms of human language, say computer code? Of course we can. In this example, the neural network is provided of an image, of a rough sketch of the website, and it generates the HTML representation of that website. It's not perfect, but it does a decent job at doing so. Can we teach machines to generate even more abstract forms of human language? For example, can we teach it how to design furniture in this case? Of course we can. In this situation, the neural network is provided with a 2D sketch of a desired furniture, and it will generate a 3D model. Moreover, that model is generated in such a way that it's actually feasible to assemble. Or in this particular case, we're telling the neural network that we would want an object that has certain physical properties and minimizes the mass. And indeed, the neural network is generating as a candidate structure that can be potentially manufactured and used as, I don't know, automotive chassis. Can we teach machines how to speak rather than how to generate text? Of course we can, because once again, we can formulate the problem as y equals f of x. Let's listen to some samples of what is possible today.
The Metamorphoses by Franz Kafka, 1915. Chapter 1. One morning, as Gregor Samsa was waking up from anxious dreams, he discovered that in bed he had been changed into a monstrous verminous bug. He lay on his arm a hard back, and saw as he lifted his head up a little, his brown, arched abdomen divided up into rigid bones.
So no longer it is a speech generator that is artificial, machine-like, what you would associate, for example, with some of the Stephen Hawking speeches. But it is a text generator that is aware of the context of the text, aware of emotions. Those tools are already used very widely to generate, for example, audiobooks, or to help mute or blind people to read to their children. Could we teach machines how to sing? Of course we can, because once again, we can formulate those problems as y equals f of x. Let's listen to some examples.
Never have much faith in love or miracles.
Is it award-winning? Definitely not. Yes, but not a single person contributed to that song. Not a single instrument was used. That audio track is entirely generated by providing a random number to a neural network.
Como casi siempre, cuando algo se muere.
Can we teach them even more abstract things? So can we teach them about humans? So in this particular example, can we teach a neural network what does it mean to have a face? Of course we can. And in this case, the neural network was designed to understand concepts of a face and is provided with that pixelated image on your left and is generating unpixelated output, injecting additional information which is not in the pixelated image. And as you can see, they are doing a fairly decent job. We can also provide them with a 2D picture of, in this case, deceased person, so Muhammad Ali, and the neural network, because it knows how a human face should look like, is capable of generating a 3D model of that face, so it can be used, I don't know, in computer games, in media entertainment content. Or we can ask neural networks to imagine faces that don't exist whatsoever. So those people were never born. Those images are a result of feeding a random number into a neural network, and were entirely imagined, if you want to use a word like that, by a neural network. Or
probably the most important thing we need to do is to bring the country together, and one of the skills that I bring to bear.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。
Somewhere over
So you can also teach them how to animate
Listen
content.
up.
2D
Train
or
your
3D.
warehouses is our main objective. Alexei, you and your men will do that.
Can we teach them about human motion? Of course we can, and indeed, that's already done in a lot of gaming studios. Neural networks are generating the movement of characters, given the shape of the terrain. Or they can do things such as interact with the environment given constraints of that environment. Let's have a quick look at this character. The motion of that character was entirely generated by a neural network. Can we teach more abstract concepts about the visual world to a neural network? Of course we can. In this particular case, the neural network is guessing the values of the missing pixels, so the white dots on your left, and generating unblurred image. This can be used to super resolve images, so transform images of low resolution into images of high resolution, or compress images. But we can also fill the missing information, like in this particular example. We remove the information from the image, and the neural network is guessing what should be most likely there. It doesn't know, so it has no clue that there should be a flag, but it will fill it with the next most likely thing. So in this particular case, soil and a bit of grass. In this particular case, we can also control this process. So we can say to the neural network, I would like some sky and some water, please, and I will place a rock here. Yep. And the neural network will guess what an image containing those objects could look like. You can also roll a dice, as you'll see in a second, to transform the image into the image in different contextual settings, but it will still comply to those required properties. Or you can ask the neural network to guess how a 2D object should look from a different perspective, from a different angle. Can we teach them about beauty and the concept of beauty? Yes, we can. And in this particular case, we're teaching the neural network to combine multiple images to create faces that are a result of mixing several different people. Let's have a quick look, and we'll quickly wrap up. I should have. So what we're seeing here is a combination of faces at the top with the face on your left. And again, those people at the bottom never existed. They are a result of combining of those two pictures. And if you think that those are just academic research studies, you're very wrong. Those solutions already form an integral part of our gaming SDK and are already embedded in a very wide range of products. And finally, we can teach them about the physical world. And in fact, the world of scientific computing and AI is merging right now. And 4 out of 5 Gordon Bell Award nominees, Gordon Bell Award is an equivalent of a Nobel Prize in the scientific community, are using neural networks or their variants to solve problems such as stability of nuclear fusion, weather prediction, earthquake simulation, or smoke and liquid propagation. And finally, my role is to help you transform your ideas into products and services. So do reach out if you have any questions about how to make your ideas a reality. We're here to help. We are vendor agnostic. We don't have a direct sales capability. We sell through partners, so companies such as IBM, Lenovo, Dell, but also Amazon, Google, Microsoft. Reach out if you need support building solutions like the ones that you saw a second ago. Thank you kindly.
Thank you, Adam. Thank you so much. Any questions? People raise their hands. Can you help me out? I was reading this book, The Imperfect in Disaster, written by an artificial intelligence agent. But what's wrong with it?
Yeah, whiskey ears, doubled builds towards deltas, it's gibberish, effectively. Yeah, this was the state of the art last year. Effectively, the discipline is progressing so quickly. You need dramatically larger models for natural language. Human language is extremely complex.
If you're interested, you can just buy them on Amazon. This one was $17, I think. So there's a whole range of books that they have.
Yeah. Hopefully,
all abracadabra, I would say.
Hopefully new editions will be better.
Yeah, I hope so. Now you've shown those crazy examples. My one question here that I have for you, Adam, because I was, I was moved by seeing AI becoming creative. And my question to you is, can you dream? Can you dream of an AI becoming an artist, and what would it mean for the future world?
I don't think it will become an artist because it is physically incapable of being creative. At this point of time, what it can do, it can, learn more or less what does it mean for something to be beautiful, and then, sample from that space. It is incapable of doing something new that it didn't see before. It's just everything that it generates is similar to something else that neural network already saw by definition.
And
but
can you dream?
Yes, I can.
Okay.
But
what are your dreams?
They are fairly random, especially about after a difficult day with my children. But what people use those tools for is to enhance their creativity, to seed new ideas. That's definitely what the community is doing.
I have written down your dream. I think one of your dreams, you say we can solve all the complex problems in the world. And I think, wow, fantastic. At the same time, I see people thinking, maybe they can also solve my job. And then you get scared. So how does this game will play out in your eyes? So
at this moment of time, we can solve really a lot of problems. And a very good heuristic of what is possible today was one given by Andrew Ng, who is a Stanford University professor. And when he's asked by the product management team when he was working at Google or later at Baidu, what is possible, he gave them a very powerful heuristic that actually works. So if a task it can be done by a human with less than 1 second of thought, it's most likely feasible to do that task, automate that task today. And we should ask ourselves a very fundamental question. Should people be doing those tedious, simple tasks? And I think the answer to that is no. The capability, their intelligence can be used in other areas much more.
And how about the task of having a chat and drinking a cup of coffee?
That's not feasible.
That's not feasible.
So services are not in huge danger. Because people will go to hairdresser to have a chat more than to have a good haircut. Because that's exactly what we're going to do now. You don't know. Thank you so much. Adam, thank you so much. Thank you.